All right, everyone. So today, like I mentioned, we're going to learn this new distribution and we're going to start chapter 12. And chapter 12, we're going to learn the goodness of fit test today. So this is the test and the scenario we're going to learn, but first we're going to talk about this new distribution we're going to work with. So the distribution is called the chi-square distribution. And of course, it's a Greek letter, and it kind of looks like x squared here, but it's kind of curved, and it's really a Greek letter, chi. So it's chi squared because it's squared. And this is the distribution we're going to talk about for the next couple lectures. So this is, of course, a distribution of squared values, as we can see in the name. This is a distribution that is for categorical data. And the categorical data will have many levels. I'm just going to say not just two. Now, we need to discuss that for a second, what that means. So far, when we studied categorical data, it was always a yes-no question, and those are my levels. So a yes, no, that means two levels, right? The answer could be two different answers, yes or no, agree or disagree, right? So now we're going to introduce more than just two levels. So I did mention this in the beginning of the semester, but something like eye color, right? So I could say, do you have blue eyes? And it's a yes, no question. That would mean two levels. Or I could say, what is your eye color? And now all of a sudden I could open it up to like four levels, right? Because it could be blue, brown, green, hazel. And so the how someone can answer the question, like how many different answers there could be, that's the levels. Right? So far we've only done yes, no questions for categorical, which is just two levels. So now we're going to explore beyond those two levels, and that's what we're going to look at with a chi-square distribution. So let me draw you a picture, and we're going to get to more about this distribution, and we'll take up a lot of paper with this. So my chi-square distribution, like I said, it's skewed right. I'm not the best at drawing this, but I will do my best. Okay, that's not too bad. My skewed right distribution. Keep in mind over here we have 0, and this is all positive values. And that is because it's squared, and I will write that down in a minute. Okay. So let me write down these characteristics of this distribution. I will shift my paper just a little bit so we can see it. So this is a skewed right distribution. It's all positive values. Since they are squared. So hopefully that makes sense. Okay. And this shape actually changes. So this distribution changes shape as degrees of freedom increase. And as it increases, it will become more symmetric. So think back to stat 1. I'm going to move this up a little bit so we can see this. think back to step 1, and we started studying the t distribution, right, for numerical data. It wasn't z anymore. We haven't looked at that yet this semester. Remember back in step 1 with that t distribution, it changed shape, right? It became more normal, it became more symmetric. It was always symmetric, but I want to say more normal, like the z curve. So taller, thinner, instead of shorter and fatter. As my degrees of freedom increase. It's the same idea behind this curve, okay? So what we're looking at, and I always try to draw this, and I really can't do a very good job with it, but I'll try. What we're looking at is that it will just kind of become a little bit more symmetric as these degrees of freedom, it kind of moves, okay, like that. As if you could see them, I just did them light dotted lines. It just kind of moves. You know, of course, I'm dramatic, right? With it, it's probably not that much, unless you have a drastic increase in degrees of freedom. But just to give you an idea. Okay, so that's what we're looking at. I need to tell you what how chi-squared is calculated, because I think it's important to you. Although we don't actually calculate it by hand because, of course, we do not need to, right? I'm sorry. So, of course, we don't need to do that. So, but I'm going to show you the calculation so we have it. And so it's chi-squared is equal to the summation of O sub I minus E sub I squared divided by E sub I. Now I'll talk to you about what all of this means, but Minitab will do all of this for us. It's just nice to know where it comes from and see the calculation. You can see the calculation's not that difficult. It's just we don't need to do it. So O sub I here, these are my observed counts. So these are what we find, our findings from our survey. Okay, we call these frequencies. And then E sub I is what we call expected counts. So with these tests, we'll have a breakdown that we're expecting to see, and we're going to compare what we expect from our survey and what we actually observe from our survey. So that's what we're doing here. And this E sub I is actually N times the probability of that, okay? And we don't need to go through all of this because we will not be doing all this. It's the probability of it occurring, okay, for our expected. And what this is doing for us, I will write this part down. This calculates how far away the observed, sorry, my little dog is barking, is from the expected. So the calculation, you can see it's calculating how far is this observed from the expected. Okay. So that's my distribution. And before we move on to the goodness of fit test that we're going to look at today, I want to go over the assumptions and the requirements for this test, because now we're looking at a new distribution. We have some new requirements we need to test for, and they look long, but they're actually very simple. It's like a quick check from our Minitab output. So it's very easy for us. So I'm going to see if I can squeeze them in here. So the requirements or the assumptions, we have two. So all expected, okay? So all expected frequencies or counts must be greater than or equal to 1. So that's a quick check. You're just going to skim it. You're going to look. Are they all greater than 1? It's a yes or no, right? That's the first one. And then this one, you have a little bit more calculation to do if it's not true, or to check to see if it's true. No more than 20% of the expected counts or frequencies can be less than 5. So I need them all to be greater than 1 for the expected counts, and no more than 20 can be less than 5. The frequency could be less than 5. So when I say it's more than just a quick little check for this one, like a skim through, because you need to know what is 20% of what you have. And we'll go through it so you can get it. It's still very quick. You just have to know, okay, well, does that mean it's one box can be less than 5, or 2 of them can be less than 5, or 5 of them can be less than 5? So you have to know what that 20% is. And then you can just quickly check it. Okay. So if you have it less than 1, then that means it's 0, and that's no good for this, right? When we're calculating. And for the second one, under 5 is considered kind of too small. And Minitab will alert us if we have any under 5. You'll notice when you work on a problem, it will say that you have something under 5, and it will kind of give you just like a little alert, so you know you need to kind of look at it a little bit harder. But these are the two things, and we will absolutely put those in our write-up. Okay. Any questions on the chi-square distribution so far? All right. Okay, so we're just letting it sink in. Once you start working on some of the problems yourself, or you see an example, I think, some questions might come up. And of course, feel free to ask in class, after class, email, whatever you got to do, okay? But don't be afraid to ask when something comes up. Okay, so now that's the distribution that we're gonna be working with for the next few days. I want to now show you this goodness of fit test. So I'm gonna show you the whole test write-up. I did take a couple things out from the last test write-up that we did, from that 2 proportions. So hopefully this makes it a little bit easier, but there are some things that are a little bit different and longer. So this is called the goodness of fit test. So in the goodness of fit test, this is a test to determine if the counts from one categorical variable differ from the expected. Breakdown or distribution. Okay, so that's the goodness of fit test is. I want you to realize what we're looking at here is we're still going to have one survey. Okay, so that means we have one sample. This is very important. So now we're noticing, okay, we will have to notice if we have what type of data, meaning numerical or categorical. And right now we're focusing on categorical. But on top of that, now we need to start noticing, okay, how many samples do we have, right? So remember last week, we did one proportion test that was one sample. Then also I did 2 proportion tests. That was 2 samples, right? 2 different populations. So, so that's now something new we have to start looking at and making sure we're paying attention to. How many samples we have, like how many populations are we studying here? Okay, so it's one survey, so we get one sample and we're studying one variable, but many levels. And my levels are K. Okay, so that's new. So I'm just going to give you verbally some examples of what we might be studying. So So many of you that have had me for step one, you know I like chocolate. I like sweets of any sort. So I always do like examples of like chocolate chip cookies or ice cream. Um, so do the counts of different M&M colors match the company's percentage breakdown, right? So if there's like 5 different colors of M&Ms, the company might say, oh, there's 10% of red, there's going to be 20% of blue, 15% of green, and make up the 100% over the colors. So if you actually took a bag and you took a sample, does the breakdown match what the company is saying? That's one type of goodness of fit test, that kind of thing. Now, obviously, that is not important, but it's just an example. Something else, and this is kind of a different way, and you're going to see you can kind of have 2 different types of goodness of fit test. Another one is do accidents on Route 390, so that's our highway here, one of them, occur with equal frequency on each day of the week. So I want to know, okay, the number of accidents that happen on that highway, do they happen the same every day of the week? Are there more on Monday, more on Thursday? That kind of thing. So that's goodness of fit, and that's the kind of stuff we're going to study and look at. So let's take a look at the complete goodness of fit test in the write-up, and then we'll walk through an example together. So this is the complete goodness of fit test that I would like to see from you. I believe this is on page 6 of our typed notes. I didn't verify that though. Okay, so we're going to start, of course, with our population step. So for a population step here, we do not need to define the objects. I'm going to just add that in here. I'll add little notes. So just, you can define the objects, but we're going to drop that for this particular test. I'm just going to write that in a different color. So this doesn't mean we're dropping this for all of our tests. For this specific test, we're going to drop that. So for my population, I'm actually going to start right with the variable. And for my variable, I want to define it, or not necessarily define it, but state the variable and how many levels. So when we're looking at categorical, a lot of times they word it as a question. It doesn't have to be. It could be a phrase or a statement. And you're just going to say, okay, 4 levels or 5 levels, 3 levels, whatever it is. Okay, we're going to start identifying that. And remember, that's how many ways something could be answered, and you'll know it. It's not going to be like a guessing game. Of course, we want to identify the unknown for the problem. So I need to define the unknown for all levels. Now, this is going to be kind of similar to what we did before for last class, where we had like P1 equals the population proportion, and it was for the one population, and then P2 is the same thing, but for the second one. It's kind of similar to that, and you can copy and paste. And of course, we'll look at that when we take a look at the example to narrow that down a little bit more to make that clear. And then my goal. Remember, my goal is really important. This matches my HA. This is what we're trying to prove. This is what we're trying to find support for, right? My goal to show support that at least one of the proportions does not follow the distribution in my null hypothesis. So this might not make a lot of sense right now, but until we get to our method step and we actually write out the null and the alternative, because this is a new test for us. But just know my goal is always to show support that that one of the proportions doesn't follow the distribution. So it means something is different. Okay, that's what we're trying to show. That's our goal, that something's different than what we thought it should be. And that's always the goal here. So it's always about not following the distribution in the null. Okay, it's always about that for my goal. And I think we're going to get some clarification when we take a look at this method step. Okay. If we take a look at this method step, so I have two situations, and so I'm going to have to show you both of them. So let me just make a note. Okay, so the first one is a specific distribution. Meaning that my null is going to be P1 equals a specific value, P2 equals a specific value, all the way up to PK, which equals a specific value. Remember, K is how many levels we have, so we're going to have that many different proportions. So if we have 4, it'd be 1, 2, 3, 4. It could be 10, it could be a lot, right? Hopefully it's not too many because that makes everything more complicated. And I'm just going to make a note here that P1 plus P2 plus P3 plus all the way up to PK is equal to 1. So all those proportions up to 100% or 1. Okay. And here, of course, like I said in my goal, my HA is at least, because if 1 is different, then more than 1's different, right? Because it adds up to 100%. So at least one proportion differs from the distribution in the null. And you can write it just like that every time. So you can write your HA just like this. It's easier actually to write it in words like this than to try to write it in symbols, because how do you pick which one's going to be different? It doesn't have to be a specific one's different. It's just you're saying, well, one of them's different. And that means if one's different, then more than one's different, since they're proportions, right? They're percentages. Okay. So that is one situation that we have with the goodness of fit test. The other one is called, so that one was specific distribution. The other situation that we have is when we have equally likely to happen across all categories distribution. So we could just say equally distributed. How about that? That's easier. Distributed. Equally distributed, meaning that they're all the same. So that was like the one with the accidents. It's all the same for every day of the week, that kind of situation. So that means that the null, and I can write it two different ways. And of course, I'm going to show you both ways because I don't care which way you write it. You could say P1 is equal to 1 divided by K. P2 is equal to 1 divided by K, all the way up to PK. PK is equal to 1 divided by K. Or you can write this. Figure out how I want to write this. Or you can write P1 equals P2 equals P3 equals all the way up to PK, which equals 1 over K. Because they all equal the same, 1 over K. So you can write it either way. Doesn't matter to me. All means the same thing. And again, my HA is the same thing, that at least one proportion differs. From the distribution in the null. So that's always the same. So my HA is the same for either situation. It's just the way I write my null. So this is something you're going to get from the problem. So the problem will say it's equally likely. Then that's when you know you have the second situation where all of the probabilities or all of the proportions, should be the same. It might just say that. It might say, well, all of the proportions are the same across all categories or something like that. It's something you're reading out of the problem. It's not really a guessing game. It's in the problem. You just have to be able to pull it out of the problem and know. And the other one, it's kind of easier to see this other one because this one, it will say, well, this is the expected breakdown, and it will give you these specific values. So of course, when we look at an example, you're going to see what I mean. And so we have either this or this, right? And those are my first two pieces. And of course, I have 4 pieces, 2 or 4 parts in this step. So of course, I want to identify what my alpha is going to be. So same idea, 5% or 1%. Usually it's 5. And I want to make sure I mention what curve I'm on. So now I need to say that I'm on the chi-square curve. So when you're typing it up, sometimes it's just easier to type out chi-square. Of course, you can find the Greek letter chi-square and put it in there. And just like when we're on the t distribution for numerical, we want to say with degrees of freedom, and we're going to, those degrees of freedom is equal to k minus 1. So it's the number of levels minus 1. So I just want to include that part with it. So this is like a little extra here, that k minus 1 there. Okay, so that's my method step. So let's take a look at my sample step. Of course, my sample step's not too bad. Like my little break in the middle of the problem. So my sample step, I'm going to include my Minitab output. Okay. Right here. I want you to notice you're going to get some graphs. You do not need to include the graphs here. So in the past, I'm thinking it's still there in Minitab 19. We get this Minitab output like we would with anything else, and then also gives us 2 graphs. I don't need to see the graphs. You can include them if you want, but you do not need to include the graphs. So I'll just write that here. So we have that to look back on in case anyone doesn't remember me saying that. We have that in the notes. So we don't need those. So you're going to paste your Minitab output. You don't need to type anything else up other than your requirement check. So this one's simple. You're going to paste your output. So of course we got to figure out the Minitab, but you're going to paste your output and then you're going to do your assumptions, your requirements. And this is just a write-up. And sometimes you can just state it all at once, or some people like to state it twice. So you're going to say that the expected counts, and you're going to check it first, right? So they must be greater than 1. That's the first one. And no more than 20% of the expected counts can be less than 5. So when you're looking at this, when I say sometimes you could just write this in one quick little statement, both of those, if you look at your expected counts and they're all greater than 5, then obviously they're all greater than 1, right? So when you look at that, and sometimes just a quick little scan, you could say, all expected counts are greater than 5, therefore I meet both requirements. Or all expected counts are greater than 5 and 1, something like that. I've met both requirements, that kind of thing. So it could be a very quick little statement. It doesn't have to be detailed, and you don't have to show me work for this. Okay, I just need you to make sure you mention it for both of those in one statement or separate it out. Either one works. So my sample step is fairly quick. It's just the mini tab that will take the longest in there. And then we can get to our results. I'm going to shorten the results step a little bit, but I'm also adding some other things. So here we're going to, just like we would with the Z, right? We just identified that Z test statistic, same idea. So we're going to identify the chi-square value. So we're going to get a value here. And we want to identify the degrees of freedom. Remember that was K minus 1. It will be given to us. It's not something you have to calculate. You'll see it. Then we're going to have a little statement to explain these. So the sum of the chi-square contributions is, and then you're going to plug in your value. This is going to be the mini tab. Chi-square value with degrees of freedom. You know me, I'm going to abbreviate, but I will write it right now. Equal to, and then it'll just be the K minus 1. So you're just explaining what those are, and that helps you understand. So I want you to know when you get this chi-square value, it's the sum of all the chi-square contributions. Remember what that is. You can kind of pull that back up. It's all of these, okay? And it's the sum of them, okay? So it's going to be the sum of all those chi-square distributions is a set value. Oops, sorry. It's a set value. You're going to plug it in here. K minus 1 is my degrees of freedom. And then you're just going to explain. So the sum, this should be capitalized. The sum of the chi-square distributions is whatever value with degrees of freedom of K minus 1. Okay. Now, of course, in my results, I want to report my p-value because that's very important for our testing process, right? So I'm going to report that p-value, and that's it. I'm going to drop the interpretation. So I'm going to write it in here that you can do it, okay? But I'll also say you do not need to interpret the p-value here. You can if you want. It's not like I would take points off if you did it, but you don't need to, okay? So you can drop that portion of the test, which is nice because that kind of gets long and tedious. Okay, so let's move on to our conclusion step. Conclusion step is the same all the time. I don't have to do anything different. I don't even really have to write this anymore, but I always will write it and include it. So the first thing is the p-value less than or equal to my alpha, right? If I respond yes, that means I can reject the null. Remember, the null means I follow that expected breakdown. If I answered no, then that means I cannot reject the null. And of course, I'm going to make my conclusion statement. So at most of the time, the 5% level of significance, the sample does or does not provide evidence to say that, and I'm gonna put my goal. Okay, so here's my goal, right? Which means that my proportions don't follow what I thought in the null, okay? Remember last class, I told you this looks exactly the same all of the time. This conclusion statement is never, I mean, I don't want to say never changes, but it doesn't change because my goal is what changes, right? My goal is what's changing from problem to problem. So if I say yes, it means I can reject. My sample does provide evidence for that goal. If I answered no, that means I cannot reject. My sample does not. So it's always the same thing, all positives or all negatives in there. And now we're going to add something else on. So plus a follow-up. So you know how we added like a follow-up statement with our CIs last class? It's kind of like that, but not really. But it's just so something extra onto our statement, okay? So plus a follow-up statement. If we reject the null. So only if we reject the null, we're going to have this follow-up statement. It's not going to be all of the time. It's only if we reject the null. Let me just write that. Only if we reject that null. And what the statement's going to be about is why are we rejecting the null? Okay, so it's kind of more of like an explanation. Like what happened? Why are we rejecting the null? So it's kind of like placing the blame on something. So something must be different, right? So the null says that, okay, it follows a specific distribution, whether if it's all the same or actually, different values, but specific. Then remember the HA is that something's different. So if we reject the null, that means our sample does provide evidence to say that something's different. If we have that scenario, we want to place the blame on something. So we want to state and notice what was different. What was so different? What is statistically different that we're rejecting our null? So basically, why are we rejecting the null? Okay. So, if we reject the null, so only when we reject the null, the follow-up statement, we just want to state what we call the greatest contributor. And why. So when I say state the greatest contributor, you're going to see which one is furthest from what we thought. So which observed value is furthest from the expected, okay? That's what we're going to do. And then we want to mention when we say y, so for the y, is it greater than? Is the observed greater or less than expected? So you're going to be very specific, and we'll see in an example. So we might say, oh, well, I thought, the percentage of blue eyes was going to be a certain percentage, and it's really different than what I thought. So that's making me reject the null. In fact, it's less than what I expected it to be. And so you'd be specific and placing the blame on a specific category, and you're going to mention that category. Okay, so is it larger or smaller than what you thought? I want to show you a picture because I love to give you guys a visual when we're studying these distributions. When we're studying this, I'm just going to squeeze it in here because it will give you an idea. At least when we're studying the chi-square distribution, what we're looking at is when we get our chi-squared number, we get this value here. I would put it down here, but I'm out of room. So this value here is going to be the chi-square, or what we call the sum of the chi-square distribution values, okay? And the p value is down in here. So that probability is down here. Okay, just so you have an idea. So remember what the alpha is. The alpha is always the area in the tails. So is alpha further here, right? So is my p-value less than my alpha, right? Then that would be a yes. I can reject. If it's not, meaning my alpha would be like in the green, in the middle of the green, right? Then my p-value would not be smaller than that. Then I would not reject my null. So that's what we're viewing. Right? I think this gives us like a nice little visual so you can picture what's happening. All right, guys, let's take a look at an example together. So I don't even know what time it is. Okay, so I'm taking a lot of time. So let's take a look at, I don't know, let me pull up my notes real quick here. I just want to see what page, because I have two different pages written down, and I think it's page 8. It's example 1, but I'm just going to quickly scroll, and before I tell you that. Oh, okay, yeah. Yes, example 1. So example 1, page 8. Sorry, I was just looking at the notes to see. Okay, so example 1, page 8, let's take a look. And I'm going to do what I did last class, where we looked at the write-up online and the type notes instead of me writing it all out, because it takes me so much time. And I don't want to waste the time. I'd rather you guys get going on your daily assignment and start practicing the work and show you. Plus, it's probably easier for you to read when it's typed rather than you viewing my handwriting. Okay, so let me share the notes. Of course, you can pull up the notes yourself on your own screen, or you can view them here with us, whatever you'd like to do. So this is example 1. So right here, it says that USA Today is studying hybrid car sales. So this was a while ago, back in 2005. So reported that the top 5 states for hybrid car sales, now this is in the beginning, in 2004, it was California, Virginia, Washington, Florida, and Maryland. So out of all the states, those are the top 5 states that had the most sales of these types of cars. So suppose that each car in a sample of for 2004 hybrid car sales classified by the states, and we took that. So the sales for the states and the other top 5 were excluded from the sample. So according to US Today in 2004, the following percentage. So California had 49%, Virginia 10, Washington 9, Florida 24, and Maryland 8%. Okay? The following table contains the numbers from 2005. So what we want to do, and we have some problems here, but what we're going to do is we want to know, is this breakdown here that we're observing in 2005, does that match the breakdown that we saw in 2004? That's what we're going to study. Now, remember, we can actually look at the percentages and see if they're fairly close, but we want to see, are they statistically close, right? Or is something statistically different? And that's what we're really studying. So that's what we're going to take a look at. So are the sales in 2005 following the same distribution as in 2004? So right there, then you can see I highlighted it in yellow, the distribution for 2004, right? The percentage breakdown. This is like that first scenario that I was telling you about, that it was it was a specific distribution, right? They're not all equal, right? It's 49, 10, 9, 24, and 8. That's not equal likely. Equal likely would be 20% for all of them. So it's definitely that top distribution and that specific distribution, that first one I showed you. And that's how you're going to know which one it is, right? So it's not a guessing game. It's here. It's just you have to read to see what it is. And then in here, sometimes we have this. So I have you do the requirements in the test. So you don't always have to answer part B separately, because you check it in the test right up. So we could probably just hit, oh, not that part. This part we could just take out, because we're gonna do that in the testing process. Okay. Remember when I asked you for a testing process, it's a complete testing process. It's not just Minitab output. I want everything. So let's take a look at the write-up for this. So we're gonna go down to the next page, of course, is where the completed example is. So remember, we don't have to complete the objects anymore. We can go right to the variable, and the variable here. So the variable is the count of hybrid cars, right? That we have, and it has 5 levels. So the variable, sometimes in these, it's easier to just make a statement than a question. So the variable that's changing, it's those car sales, right? The hybrid car sales, or the counts of it, you can say. And what is the levels is how many states we're studying, and that's 5. So now you're going to see how I define my unknown. So it's not just P1, P2, P3, P4, P5, right? It's PCA for California. And it's the population proportion or true proportion of hybrid car sales in California. So you can see how it's going to be the same thing, but I'm just going to change it for which state we're studying. So it's the proportion of those car sales in each of those states. Okay? So that's why I was saying it's kind of similar to what we did with the 2 populations where you could copy and paste it. But we do want to define all of these. I would rather see you use specific notation like this to make it clear rather than just 1, 2, 3, 4, 5. But if you use 1, 2, 3, 4, 5, it is okay. I just prefer this way because you are defining it. So just make sure you always define what you have so whoever's reading it knows what these stand for. And of course, the goal. So the goal is always for the HA, and the HA is to say that something's different. So right here, the goal is the hybrid car sales in 2005 do not follow the same distribution as in 2004. So that's one clear statement, right? Or you can write it in a different way. You can say at least one of the proportion of hybrid car sales differs from the given proportional values. So you can write it a couple different ways. I'm just giving you a couple examples of how you could write it here. You don't have to follow the same way, but remember the goal is always about it, the proportion, at least one of the proportions differing from the null. All right. My method. So remember how we had the 2 situations. We just talked about how it's a specific breakdown. So my null matches the breakdown from 2004 that was given to me, those percentages. So it's P of CA is equal to 0.49, then Virginia 0.1, right? And so it's the percentages just written as decimal form. And then my HA, as I said, and it's always going to be the same, at least one proportion of the hybrid car sales differs from the null. If you didn't put the context in there, it would be okay. If you said at least one of the proportions differ from the null, I would be okay with that. Just remember the goal should be specific to the context. I wouldn't be so picky about it in the HA, but I do include the context here. My alpha is 5% because it's not medical, life or death. I'm on the chi-square curve with degrees of freedom equals to k minus 1. That's all you have to put. You don't actually have to put k. You don't have to put 4. You don't have to put 5 minus 1 here yet. You will put that in your results step. So just k minus 1, just noting that you have degrees of freedom. Now, my sample step, I'm going to put my Minitab output. So let's go ahead and switch our screens over to Minitab. And I don't have any data. Let me see before I say that. I do. Okay. So if you guys want to open up your data, it's right below the typed notes in day 7. So feel free to do that. I'm gonna share my screen with you. I'm going to share, or stop sharing. I'm gonna reshare this, my Minitab, and it has the data. Now, it's like a table. Okay, so now you should be able to see this. It has California, has observed counts, expected counts, right? My expected, those are percentages, so they're decimal form. Observed are just numbers. If you weren't given this Minitab table already typed up in Minitab, you could easily type this up, right? There's like 15 little spots to type in, little cells. There's not a lot of information in this one. So you could easily open up just a new Minitab screen and type in your states, your observed, and your expected. All right, so now we have this mini tab. So we will start by going to stat. When I click on stat, we're going to go down to table. So it's the fourth from the bottom, so about 25% of the way up. Okay. And under tables, you're going to see there's a couple different things that say chi-squared, but look at the one second from the bottom. Chi-square goodness of fit. So that's the one we're going to click on, since that's the test we're doing. I thought it disappeared, but then I actually clicked on it, I guess. Okay, so we're here, chi-squared goodness of fit test. And you can see it wants to know the observed counts, right? So what it wants to know is, where are these observed counts? What are these observed counts? So if I click on that box, then you'll see this will pop up. Well, I already have it labeled really nicely in the mini tab, so I can just double click and bring it over. That's my observed counts. I can name this. So remember, graphs are going to pop up, so I can name it if I want. You do not need to do that. You don't need to do that to get your information out that you need. Okay, you can, if you want, like you can say, okay, it's state. Whoops. The states, right? You can do that, or just state, but you don't have to do that. Now, if I clicked on my categorical data here, we would use this box or this portion right here if we're using raw data. Okay, so just keep that in mind. When we're using raw data, then we would use this. We don't have raw data. We have like this table, right, with these tallies. So we don't have that. So we don't need to do the raw data thing there, but we might need it at some point.
Professor, this is the caption. Can you?
Yep, I'm switching you. I'm just
Thank
pulling
you.
it up. Just give me a second. Okay. So I don't need to do anything with that there. I'm just gonna go back to here. Okay. All right. So now in my test process, I need to know, okay, do I have equal proportions or do I have specific proportions? So equal proportions would mean that all of the levels are 20%. So it would mean my expected would say down here would say 0.2, 0.2, 0.2, 0.2, right? That would be equal proportions. And I, in fact, wouldn't even need this column in that case. Specific proportions mean that they're different and it's this specific breakdown. So I'm going to click on that. I'm going to click in the box and then I can tell it, okay, those are my expected breakdowns, and bring those over. Okay. All right, so here, then I have I can just go ahead and click OK. You can play with stuff in here, because I think if you go into graphs, you could tell it not to give you the graphs. I don't bother with them. Because I don't need them. They're going to give them to me, but I don't really need them. It doesn't matter. So I can just click OK, and I'll just do that for now. But remember, you can always play with the output and, see what it looks like and what things change. As you can see, this output, it's going to look so different from what we're used to seeing last week and the week before. So I have this like table, and we're going to look at what we could do with that table. You can see I have my chi-square test. Look at N. So I have 406 values. DF, degrees of freedom, which is 4. We should have known that already because we had 5 levels, and then DF is K minus 5. So it's, I'm sorry, K minus 1. So it's 5 minus 1, which gives me the 4. Here's my chi-square, my sum of my chi-square. This is the value I'm going to report in my results. And look at my p-value. It's very small. It's not 0. It's just really small number. I'm going to expand it so we could just see that. Wow, it's real small. Okay, so just so we can see that. So of course, what I do is I copy and paste and bring all of this over into my my Word document. But what I was saying about the graphs, these are the graphs. So it gives you a nice visual, and include them if you want, but I don't need to see the graphs. So you do not need to include these for me. Okay, just so you know. When we labeled that, I'm trying to think of where that comes in, the state for that categorical. I mean, it says it up here, but I feel like there was another place, and I don't know if it was just for the graphs. I don't know. I'm not seeing anything where it came in. But anyways, so you could see why that's optional. It didn't even help us here. Okay. All right, I'm going to copy and bring this over. We'll take a look back at the write-up in the day 7 notes. So I brought this over. Now for this one, a lot of the times I actually bring it over where I do that send to Word. So where I click on that box, the drop down arrow, and I have all the different options, and it says you copy, send to Word. Remember, if you send to Word, wherever you left your cursor in your Word doc, it will send it right over. And the reason why I like it is like this example here. So when I did that here, then I can actually highlight these, right? See, I sent that to Word. If you had a picture, it would just be one picture here. The bad part is I can't really resize things easily. I mean, you can a little bit, but it gets distorted. But I can highlight things, okay? And you can see I highlighted things here, and we'll talk about that in just a second when we need these numbers. Okay, so there's that. Now here's my requirement checks. What I'm looking at is my expected. Look at, it's this column right here. So all of this right here in gray that I just highlighted in gray, that's my expected counts. My expected counts. Now every value there needs to be above 1, and no more than 20% could be below 5. Now 20% of these categories, right? So I have 1, 2, 3, 4, 5 categories, right? 20% would mean 1 category. So I'm allowed to have one of these state categories to be less than 5, but I couldn't have 2. That's what we're looking for. So that's why I say it's a quick check, but you have to kind of figure out in your own mind, okay, what is the 20%? So I have 5 levels. So 20% of that is one of them. So one of those could be less than 5, and I would be still okay with my requirements. But we can look, they're all above 5. I mean, they're all above 32 even. So this is my quick statement. All expected counts are greater than 1 and none are below 5. And I just do a little check mark like, okay, I've checked my requirements. Okay. If you feel better about writing up separately, that's fine. But I'll tell you, most students just end up doing a brief little statement like this, and it just checks both requirements. So that's my sample step. It's really quick. My result step. Now I'm going to use the information I got from my sample step. So here you're going to see, so I really would like to see, at least at first, the chi-square equals, this doesn't need to be bold, or as big as it is, I guess. Okay, my chi-square contribution. This is the number in the chi-square test output. So that is the 61.7475 value. And then I just say degrees of freedom equal. Now it's the k minus 1. So you can say 5 minus 1 equals 4, or you could just simply say 4. It's given to you here. I don't expect you to say 5 minus 1. I'm just going to say 4. Okay. Now the statement you want to say, the sum of the chi-squared contributions is 61.7475 with 4 degrees of freedom. So for today, let's report the chi-square and the degrees of freedom, and we could probably drop it after a little while, but we'll just report it for today at least, and then we can start, doing this. When I mean that, only doing that. But let's do the 3, okay, where we report it, and then we have the write-up, and then we report the p-value, which of course is very small. All right, let's do the conclusion. So yes, our p-value is less than alpha because it's very small. We can reject the null. So at the 5% level of significance, the sample does provide evidence to say that the hybrid car sales in 2005 does not follow the same distribution as it does in 2004. So that's what we're saying. It doesn't follow it. Something is different. So if something is different, I need to explain what is different. I need that follow-up statement. The follow-up statement's about the greatest contributor. So let's go ahead and look at the output to see what that greatest contributor is. So when I'm looking here, I'm looking at the contribution to chi-squared. So it's this very last column. This contribution for chi-squared, I'm looking for the largest number. The largest number is representing which one is furthest from the expected. And I highlighted it here in yellow. It's Florida. Look at that number is 42. So that means the difference from my observed from what was expected is the greatest there. That's my greatest contributor. So I look at that and I say, okay, it's Florida. Florida is my greatest contributor. Now I want to say, what was it? Is it higher or lower than what I expected? Okay, so let's take a look. My observed was 33. My expected was 97. I thought it was going to be 97 sales and it was only 33. So it's less than. And that's all I'm going to mention. So it's a quick look. It sounds like it's longer than it is. It's actually really quick. So I just say the greatest contributor to chi-squared is Florida, where what was expected was larger than what was observed. Or you could say what was observed was smaller than what we expected. And that would be my write-up. So that would be my write-up for my full hypothesis test with that full conclusion. Are there any questions on this?